Welcome everyone, welcome to module 12. So in today's class we'll be seeing analogous systems. So we'll wait for a few minutes for other students to join and we'll begin our class sharply at 6:05 p.m. Okay, so let us start. So in module 12, we'll be looking for analogous system. That is how we can transform any mechanical input as an electrical output. So this chapter is very important for the perspective of control system and designing some control system devices. So let us have a brief introduction about modeling of mechanical systems. So a mechanical system is generally having some moving parts and we are trying to calibrate that distance or space of velocity that moving part is giving into some electrical signal. So for example, if we know a force is acting on certain body, so by Newton's law, second law, that is Newton's second law, we have force is directly proportional to the acceleration and where mass is the proportionality constant. So we can write d square x by dt square, that where x is the any kind of displacement. So in similar fashion, we can write all mechanical system in terms of a partial differential equation. So let us first of all define what is a partial differential equation, or a PDE. So a partial differential equation, so here we have written is an ordinary equation, ordinary differential equation. So the main difference between an ordinary differential equation and a partial differential equation is that in case of partial differential equation, we first of all use a symbol known as dou. So for example, dou by dou x of any quantity. Let us suppose we are writing for velocity. So velocity will be change in displacement with respect to time, dou dx by dt. And in terms of ordinary differential equation, we'll write v is equal to dx by dt. The major thing here is that in case of partial differential is that all the other parameters here are kept constant. So suppose if we have some physical parameters associated with this, such as let us say volume, pressure, anything. So all these quantities are kept constant while differentiating for any displacement. Whereas in case of ordinary differential equation, the other values may or may not be constant. So therefore, this partial differential term comes in handy. So the major challenge here for converting from a mechanical system to electrical signal is that the electrical signal is generally based on digital output. So a digital signal like this, that is 0 or 1. So all of our electronics devices are based on a binary signal, which is low input or low or high input. So whereas any mechanical system here are analog in nature. So a mechanical system here is a analog signal. So analog signal to digital signal, we have to calibrate our system because we are transforming any mechanical motion into an electrical signal. And in case of electrical, we are using digital signals because of major advantages, such as in communication purpose, or in case of signal transfer, the transfer of digital signal is beneficial. Also, the amount of noise in case of digital signal is very low as compared to in case of analog signal. So let us first of all define the mechanical systems here. So by definition, mass is considered a property of an element that stores kinetic energy of translational motion. So here this is a relation between mass and weight. So weight is actually a kind of a force, that is mass times the universal mass times the acceleration due to gravity constant g. So I think you all are aware with this relation. So the mass of a body is a constant quantity and it doesn't depend upon where you are going to measure it. But the g value on Earth is around 9.8 meter per second square. So the weight becomes mass times g. So the equation of linear mechanical system are written by first constructing a model of a system containing interconnected linear elements, and then by applying a Newton's law of motion in case of a mechanical system. So the step is that first of all we have to draw a free body diagram. So a free body diagram is basically we focus on a mass m or object m with mass m, and we try to find out all the forces acting over it or the force that it is applying to some other objects. So for example, let us say force F1 is applied along this direction, and along the negative y-axis we have force 2, and we have force 3 along the positive x-axis, and we have force 4 along the negative x-axis. Now the direction of force has to be considered here, so the vector sum of all those three forces should be equal to 0. So let us take a convention that force coming inward force we will take as positive. So F1 is inward to mass m, so it will be F1 positive. F2 is again going away, so it will be minus of F2. F3 is going away, so minus F3, and F4 is also going away, so minus F4 is equal to 0. So the force is a vector quantity, so that is why there is a vector notation. So from this relation we can say that force F1 is equal to F2 plus F3 plus F4. So the motion of mechanical elements can be described in various dimensions. So now the motion, because of this force applied, can be of different types. Translational motion, in case when there is only a linear transfer, that is the change in x or y or z component of the coordinate system. In case of Cartesian plane, then we say that this is a translational motion. And whenever the body rotates around its axis or any other axis, then in that case we say that the motion is rotational in nature. So the xyz, that is a Cartesian geometry generally used for translational, and in case of rotational, it depends. We generally use polar coordinates with r and theta in two-dimensional system, and for three-dimensional system r, theta and z will be there. So the equation of now we know the force balance at the free body diagram. Using the free body diagram we know the force balance, so now we can convert this equation in terms of a partial differential equation. So let us first of all focus on the translational motion part. So the motion of translation is defined as a motion that takes place along a straight or curved path, that is, there is a change in the xyz component. So the variables that are used to describe translation motions are acceleration, velocity and displacement. So let us define these three components. First one is displacement. So displacement is the net change in the position of an object. So suppose it is the shortest path. So suppose we have an object at some point x1, y1, z1, and it moves to x2, y2, z2, then the shortest path will be a straight line. So this is the displacement between point A and point B. Again, displacement is a vector quantity, that is, it will have all the three components, that is I, J and K. The second term here is velocity. So again, rate of change of displacement per unit time is velocity. So the relation between velocity is that v is equal to dou x by dou t. Or suppose we write this in a vector form, so s is represented by displacement, that is x. So let us call this xi plus yj plus zk. This is a displacement vector. So velocity will be dou of s by dou t. And similarly, if we double differentiate it again, we'll get the acceleration, that is dou square s by dou t square. So acceleration is rate of change of velocity with respect to time. So this was about the translational motion. So already discussed about the Newton's second law. All the sum of all the forces should be equal to mass times acceleration for a body. So if acceleration is 0, we say that the body is rigid and there is no motion. The body is not in motion, the body is in a rest, state of rest. Of course, these all parameters are with respect to a certain reference point. So let us see an example here. So we have a free body diagram for a mass m. So this is the object of mass m, and m denotes the mass, a is the acceleration in the direction considered. Figure 1 illustrates the situation when a force is acting on a body with mass m. The force equation is written as, so from the Newton's second law they have written force is a function of time here, because acceleration is given as a function of time. Mass is a constant quantity, and we can write acceleration as dou O square. So here they are taking this as y, displacement is given by yt by dou t square. This can also be written in terms of velocity as m into dou v of t by dou t. So these are the two partial differential equations. The first one is a second order PT, and this one is rather a first order PT. So for linear translational motion, in addition to the mass, the following system elements are involved. So we'll study different cases here. So the first case here is a spring. So we all know the Hooke's law. So the Hooke's law states that force is equal to k times displacement, or it can be written as force is a function of time, where force is equal to k times yt, where k is the spring constant. So k is the spring constant, or simply defined as stiffness. So this equation 4, implies that the force acting on the spring is directly proportional to the displacement of the spring, and the model representing a linear spring. So again, this is not a partial differential equation, because the relationship here is a linear relation. So when we say a function is linear, so this is a definition for linearity. So whenever f of any function f with domain t1 plus the other same function with other domain t2 is equal to f of t1 plus t2, whenever this relation is established, we say that the function is linear. So let us quickly check for our function whether this follows linearity or not. So using the function, f of t1 will be equal to k of y of t1. Okay, f of t2 will be equal to k into y of t2, and f of t1 plus t2 is equal to k into y of t1 plus t2. So let us say this 1, 2 and 3. So adding 1 and 2 will get f of t1 plus f of t2 is equal to k times y of t1 plus y of t2. And so y of t1 plus y of t2 has to be equal to y of t1 plus t2. Why? Because this y is a displacement term. So displacement is always the shortest path. So let us suppose we have two objects. Let us suppose we have two objects. First of all, we have a motion S1 and other has motion S2. So these two are the displacement, and S1 plus S2 is always equal to S. It is the net distance. This follows the vector law of addition. So therefore, this follows the principle of linearity. So now suppose the spring is loaded by a mass. So this is our spring, and we are loading it with a mass m, and the spring is attached to a rigid surface, that is an immovable surface. So in that case, we can write this f of t minus t is equal to k times y of t. So where tension T is because of the mass. So friction, now we'll move to friction. So whenever there is a motion, there is a tendency to restrict that motion. So whenever there is a motion or tendency of motion between two physical elements, friction force exists. Friction force encountered in physical system are usually of non-linear nature. Correct. So friction force are in non-linear form. The characteristics of the friction force between the two contacting surface often depends on the surface as composition of surface. So suppose we have two surfaces. One surface is a rough surface, other surface is a smooth surface. So in that case, the frictional coefficient mu, in case of rough surface will be higher as compared to in case of a smooth surface. So whenever we have a rough surface, the frictional force, if the velocity movement is along this direction, then the frictional force will act opposite and it will be higher. So three different type of frictions are commonly used in the practical system: viscous friction, static friction, and Coulomb friction. So viscous friction is generally used for liquids. In liquid flowing over a surface. Static friction is the amount of friction that is required to break the state of motion. So that is, if a system is in rest, if it has to move and gain some velocity, it has to overcome that static friction. So let us see about the viscous friction. Viscous friction represents a retarding force, that is linear relationship between the applied force and velocity. The schematic diagram element for the viscous friction is often represented by dashpot shown in figure 3. The mathematical expression for viscous force is fixed friction is f of t is equal to b times the ordinary differentiation of displacement with respect to time, where b is the viscous friction coefficient. Okay, so this is again clear that viscous friction generally follows this linear relationship and is given by equation 6. Here b is the viscous friction coefficient. So here this is given a free body diagram. So y of t is the displacement along the positive x-axis. So in that case, f of t is equal to b times dy by dt. So static friction represents a retarding force that tends to prevent the motion from the beginning, and it acts always in the opposite direction of the motion. It is defined as a frictional force that exists only when the body is stationary but has a tendency to move. So whenever they are trying to break the state of motion. So the sign of the friction depends on direction of motion or the initial direction of velocity. Once the motion begins, the static friction force vanishes and other frictions take over. So static friction is only active until the body is in rest. Once we overcome the static frictional force, it vanishes. And the third one is the Coulomb friction. So Coulomb friction is again a retarding force that has a constant amplitude with respect to change of velocity, but the sign of frictional force changes with a reversal of direction of velocity. So again, this force acts always opposite to the direction of velocity. So the three types of friction cited here are merely practical. So all these forces are a practical model. So we have classified them as in three categories: to model the system and to convert that mechanical system into electrical signal. So all these are models. So a model can never predict the actual practical thing, but we can predict more and more closely to the realistic situation. So in many unusual situations, we have to use other frictional models. So there are a number of models available, so we'll be generally shifting to those as per the requirement. So table 1 shows the basic translational mechanical system properties with their corresponding basic units. So mass represented by M, capital M, is having a unit of kilogram kg. Distance will be represented by y in meters. Velocity is v, meter rate of change of distance per rate of change of displacement with respect to time, so meter per second. Acceleration a, meter per second square. Force is in Newton. Spring constant is in Newton per meter. And the viscous friction coefficient b is Newton per meter per second. So let us see an example here. So consider the mass spring friction system shown in figure 1a. The linear motion concerned in the horizontal direction. The free body diagram of the system is shown in figure 1b. So this is the system. So a mass M is there. We have a spring attached to it. A frictional component, viscous frictional component is attached, and the motion is taken, force is taken in direction of positive x-axis. So this is the free energy diagram. So sum of all these components should be equal to 0. So f of t should be equal to k pi of t plus p into dy t by dt. So this is again a differential equation. So the force equation here is written, and we converted the components here. So f of t minus b into dy by dt minus k into dy by dt is equal to mass into acceleration, that is m into d square yt by dt square. So this is the term if there is motion, that is f is equal to m. So let us rearrange the equation. So we'll get a second order differential equation, ordinary differential equation. So this is the equation for the motion of an object under spring and viscous forces. So here again we will use this notation y dot of t for dy by dt and y double dot of t for second order differential. So substituting these two symbols in our equation, the equation can be written in this form. So here yt is the output, and so yt is the displacement output, and f of t by m is the considered input, the input force that we have applied to the system. So now to solve this differential equation, we need some boundary conditions and some initial conditions. So let us take the Laplace transform for the system. So in case of a double differential, we will have s square, and in case of single differential, we will have 1 by s. So for zero initial condition, the transfer function between ys and fs is given by this. So we have transformed this into a Laplace transform. So this comes out to be ys by fs is equal to 1 upon ms square by bs plus k. So now from control system perspective, we can draw the block diagram to represent the system. So here f of s is the input and y of s is the output. So if we can write here in the feedback loop, f of s minus y of s times k minus b times So this will be so let us say this term here is R of S. So R of S times 1 upon M into S itna is equal to R of S. So this is the output R of S. So let us take R of S in the RHS form. So F of S minus Y of S into K is equal to R of S B by M into S plus 1. So this is the relation here between F of S and R of S, but we also know a relation between R of S and Y of S. So let us find the relation between F of S and Y of S. So at this point we are having R of S into 1 by ms times I of S is equal to Y of S. So this is a straight loop, no feedback loop is given after R of S part. So let us substitute R of S above and we'll arrive at F of S minus Y of S K is equal to R of S is Y of S by into ms square by I times B by ms plus 1. So this is a relation between F of S and Y of S. So here they have tried to solve this with x component in two directions, that is x1 and x2, with we are having y of t is equal to x1 and y dot t is equal to x2. This is the first order and this is the second order. Sorry, this is the first 0th order and this is the first order. So the u of t function can be written as f of t by m. So finally we can write in this matrix format the given partial differential equation for yt and y dot t. So these are y dot t, x1 dot is y dot t and x2 dot is equal to y double dot t. So finally we arrive to equation number 9. So this equation 9 now has to be solved for, so that there are two matrices, so we'll get two differential equations, one for x1 dot and one for x2 dot. So these are the two equations we'll try to solve. And now applying the zero initial condition at t equals to 0, we are applying the initial zero condition, that is from the Laplace transform 1 by s is equal to 0. So finally we obtain the transfer function y of s by x of s is equal to ms square by bs plus k. So again the same results can be applied from the gain formula of the logarithm representation shown in equation 11. Okay, so therefore we arrive at the transfer function y of s by x of s. So this was for the zero initial condition, but for the initial condition is non-zero. So again in that case we have to take the initial condition. So this is the initial condition being represented. x10 is the initial condition. I see. So With initial condition, we have tried to solve the problem, and with initial condition again we substitute the value of x1s. So on substituting x1s, here we can write it either as x times x2 minus x2 0. So on simplifying this equation, we can again draw the block diagram as shown here in figure 4, and the output now is this function. So this is the Laplace transform of the output for the given mechanical system. So that was the translational motion. Now we'll move on to rotational motion. So let us take a break for 2 minutes here, and we'll start with rotational motion. So welcome back. We'll start with rotational motion now. So rotational motion can be defined as a motion about a fixed axis. So motion of the object around any fixed axis is termed as rotational motion. So it can be either clockwise or anti-clockwise. So the extension of Newton's law of motion of rotational motion states that the algebraic sum of the moments or the torques about the fixed axis is equal to the product of inertia and the angular acceleration about the axis. Sum of all the torques is equal to j times alpha. So where j is the inertia and alpha is the angular acceleration. So the other variables used will be the torque tau, angular velocity omega, and angular displacement theta. So if we draw analogous to the translational motion, so theta is the displacement, omega is the velocity, and tau is kind of a force in case of translational motion. Okay, so the approach will be same here. Let us first of all define all these components one by one. So the first one is the inertia. So inertia is considered a property of an element that stores kinetic energy of rotational motion. So earlier mass was the property that stored energy due to translational motion. So inertia of a given event depends upon the geometric composition about the axis of rotation. So for instance, the inertia of a circular disc or shaft of radius r and mass m about its geometric axis is given by, so moment of inertia or J is equal to half mr square. So where m is the mass and r is the radius. So suppose we have an axis, we have some object at a distance r, of mass is m, some object is of mass m1 r1, m2 r2. So in that case the summation will be half m1 r1 square plus half m2 r2 square, and so on up to n particle will have n. So whenever a torque is applied to a object body with inertia J as shown in figure, the torque equation is written in this form as given in equation 3. So torque is J times alpha t, and alpha t is equal to d omega by dt, and finally we can write it in second order as d square theta by dt square. So theta is the angular displacement, omega is the angular velocity, and alpha is the angular acceleration. So again it follows the similar terminology as discussed in the translational motion. So now we have a torsional spring. So as with linear spring of translational motion, a torsional spring constant K. So this is again analogous to our linear spring. So torque per unit angular displacement can be devised to represent the compliance of a rod or a shaft when it is subject to an applied torque. So tau is equal to K times theta t, where K is the torsional spring constant. So we can write this for any preloaded torque. So in case of any preloaded torque, we will subtract the preloaded torque tau p with the torque, and that will be equal to K times theta t. So now again in this case we'll have frictions affecting the rotation. So again the same three component of frictions models are available here. So the viscous friction is given as tau of t is equal to p times change in angular velocity, angular movement. So theta here is given by the displacement, angular displacement, change in angular displacement per unit time, p times. And static friction again will be opposite of the direction of rotation, and Coulomb and will only act up to rest part. And Coulomb friction is again acts in under rotational motion. So under rotational motion, it acts opposite to the direction of rotation. So the unit table again here is listed. So please go through this unit table. So inertia is given by J as a unit of kg meter square. Angular displacement tau is in radians. The angular velocity again in radian per second. Angular acceleration, so I think there is an error here. This is tau, this is omega, angular displacement is theta, angular acceleration is alpha, and angular velocity is omega. There has been some typing error. And torque is tau, not t. Spring constant is k, and viscous friction coefficient p, and energy is q. Okay. So here is an example here. So in the given figure or diagram, a motor is coupled to a load through a shaft with a spring constant K. A non-rigid coupling between two mechanical components is in a control system often cause torsional resistance that can be transmitted to all parts of the system. So this is an example of a rotational system. So the motor is trying to rotate the load. So here the torque is given, angular displacement is also given, moment of inertia Gm is given, and the viscous friction coefficient Pm is given. So spring constant given is K, and we have a load. So the load angular displacement is theta L. This is load, and this was source. Motor is the source for mechanical motion, and GL is the moment at the load. So these are all the variables. So actually I listed earlier previously. So again, please go through the list of variables. Okay, so I hope you have gone through this list. So let us now move to writing the equations. So we can write from the free point diagram of the system at the motor end. So the net change in angular displacement, that is the double differential, here is representing the alpha, that is the angular acceleration. So angular acceleration is equal to, this is the frictional part, minus Bm by Gm, differential of theta by dt. This is the spring component part. So the spring component part, so here you can say that the direction is opposite. Theta is moving in clockwise and this one is moving in anti-clockwise direction. So theta m minus theta l is the net times k times Jm. K is the spring constant, and now plus adding the load component. So load is 1 upon Jm by tau m. So we can write this here in terms, is a function here. So this d square theta term we are taking in the RHS side, and all the other friction and load components due to angular displacement parts are listed in the LHS side. So we arrived at equation number 2. So in case of such systems where we have three variables, that is three storage elements, Gm, Gl and K, thus we require three equations to solve for such arrangement. So equation 1 and 2, we are now rearranging 1 and 2 to get 3 and 4. So equation 4 here again is similar to equation number 2, just we have rearranged it. And equation 1 here is this one. So we have now the angular displacement at the motor component and at the load component. So now the state variables can be written, that is x1, x2 and x3. So the state equations are written here in equation number 5. So these are the state equations. So now we have to simultaneously solve these three state equations to arrive at the transfer function. So this is the free body cylinder flow diagram. So this looks complicated, but if we write at equations at all each nodes, we'll arrive at the similar equation set of state equations. So I'll not go in detail of explaining this. You can try of your own. So this transfer function for so this is the third example for today. So these are all solved example. You can look in the notes. So the transfer function of a simple liquid system is given. So we have a tap here, a pipeline through which water is flowing in this bucket, and we can model it in an electrical manner. So any storage of water is related to the capacitance. So for example, the capacitor stores charge. That is why we have capacitance, and any friction is given by resistor. So a resistor opposes the flow. So that is why we have a resistor R. So steady flow rate Q is given. Q and small q is the small change in the inflow. Q naught is the small change in the outflow. So these are the Q's. So steady flow is Q. So the inflow will be adding it. So it will be Qi, and in the outflow we will be subtracting Q. So the direction will be plus, and this will take care of itself. And H is the steady state head before any change, and H is the small change in the steady state. So we do not assume any turbulent flow, so all the turbulence is linearized. So these are all assumptions. So now we can write the equation for the capacitance. So C into, so this height H. So as height H increases with respect to time, there is a change in the inflow and outflow will be equal to the change in the height of the container. So not container, the height of the flow, height of the water stored. So as the inflow and outflow difference increases, so inflow is higher and outflow is lesser, in that case the water will fill up. And if the outflow is higher, inflow is lesser, in that case this will go down. So this can be written simplified here and written as this. So this is first equation. So now from the definitions, capital R is defined as a change in the level difference in meter divided by the change in flow rate in meter cube per second. So meter cube per second is the volumetric change per second. C here is defined as the change in the liquid stored in meter cube. It is the volumetric change divided by the change in the head in meter. So this is change in head A delta H. So now we have already arrived to this equation. C times TH is equal to the difference in the head Qi minus H by R dt. So from this we can simplify this and write the equation. So this is a RC circuit example, R and C. So taking the Laplace here, so taking the Laplace will taking the Laplace here. So from the Laplace we can, this is the partial differential equation, and finally this is the Laplace. So again we take the transfer function Hs by Qis is equal to R upon 1 plus SRC, and the output of the system will become Hs by R. So Q output by Q input, that is give us the final transfer function is equal to 1 upon 1 plus SRC. So In this way we can transform any mechanical system into an electrical system. So mechanical to electrical transformation was understood briefly here. So I didn't want to solve the problems here because this part of the section is just for a brief. You will get much better details about these topics in control system. So there is a subject called control system. I think you'll get it in third year or maybe second year. So just a brief outlook about how the transfer of mechanical moving part, that is translational and rotational moving parts, we can transform it into electrical components. We can represent it with the help of resistor and capacitor, and some cases it is an inductor. Okay, so this was the last module, module number 12. Hopefully we'll meet next semester if you join the course. Thank you for joining this course, and I look to see you in the next semester. So with this, I'll end today's class and also the module for basic electric circuit course code EE93. Okay, thank you all.